Hi, let us try another example. We are dealing with the same column. The specifications and the details are the same, except that the conditions for the columns are slightly different. The structures is braced, the columns is slender, the slenderness ratio and the effective lengths are given. The loadings are the same, except that the moment is acting in the minor axis. This example is meant to demonstrate the differences in terms of the calculations when the moment is acting in the minor axis of the column. Since the details and the specifications are more or less the same, our following discussions shall concentrate on the unique design step as compared to the previous example. As for those common design steps, if you wish to know more, you may refer to the previous videos. Based on the specifications and the details given, we know that this is a slender column, braced structures, uniaxial load, and the moment is acting in the minor axis of the column. First, we deal with the concrete cover. The concrete cover is 35 mm. Slender column, braced structure. That means we are talking about these equations to determine the MED. Again, you are encouraged to sketch the stress diagram for you to work out the equations in order to determine the MED for the braced column under slender conditions. There will be first order moment. Since the MED is calculated on the basis of M02 MOE plus M2 M01 plus 0.5 M2 and Min. That means you will need to get at least 3 first order moments, which are M02, MOE and M01. M02 and M01s are calculated based on the moment obtained from the column plus the moment due to the imperfection. Therefore, you will need to calculate the imperfection moment. NED is given, which is 49.12. EI is calculated based on the effective length divided by 400. The effective length is given 2-point-something meter, which was adopted from our previous questions. Now we are designing in the minor axis. Braced structures, minor axis, effective length is 2-point-something meter. As for the slenderness ratio, 48.5. Substitute the L0 divided by 400. You get EI equals to 5.2. Multiply this EI with the axial load, 49.12 kN. You get the moment due to imperfections. The moment due to imperfections are to be added up with the moment given in the questions, which are 13.3 kN and 7.5 kN. That gives you slightly higher M01 and M02. You will need to get the M01 and M02 correct, as you need them to calculate the M0E, which is 60% of M02 plus 40% of M01. This calculated value will need to be compared with 40% of the M02. Choose the bigger value. You get M0E to be equals to 11.3. Now if you observe the calculation step, this process will be the same for the slender columns, regardless it is braced or unbraced. You can do the same for the short column, where you get the M02, M01 and MOE. But you know that this is not likely to be the most critical one, even though you calculate this. But at the end of the day, the calculated MED shall not be governed by the MOE. Therefore, you don't have to find this MOE for the short column. In fact, you don't need to get this MOE also for the umbrella structure, since the final equation here is not governed by MOE. That means this MOE it shall be unique to the slender and brace column. Once you have acquired the first order moment, we shall look into the second order moment. From the sketch here, you see the second order moment, M2 here, and these two shall be half of the M2. Later, when you superimpose them, on the top side, bottom side, as well as on the MOE side, you can work out the equations for MED. Now, the largest MED may happen anywhere among these three. Therefore, you will need to calculate all of them. Now, the problem here is, for you to calculate this M2, you need eccentricity E2. To get the E2 here, you need to go through a series of equations. It is not really hard to go through these equations, as long as you know the symbol and you know where to get those values. By referring to the flow chart here, you can produce E2. Only that you need to pay attention on the correction factor Kr here. Since you are asked to design for the reinforcement bar for this member, that means at the moment you don't know the amount non-reinforcement. Not knowing the amount non-reinforcement bar, that means the AS here shall remain unknown. As a result, you don't get the omega, and then you don't have NU, and you don't know what is the Kr. Not knowing the Kr, you cannot get the curvature ratio, and you cannot get the E2, and you don't know the second order moment. Since we do not know the amount of reinforcement bar, what is for sure, this definitely shouldn't be equals to 0. That means ultimately it may end up to be a certain value, which at the moment we do not know what is the actual value. Therefore, our calculation steps shall normally start with assuming the Kr equals to 1.0. This process is similar to the questions that we did previously regarding the slender column of the umbrella structure with the moment acting in the major axis. Let us come back to this question. You don't know the reinforcement, therefore you assume the Kr equals to 1.0. Having the Kr settled, you will need to find the value for the K5 and also 1 per R0. Maybe we start with finding this 1 per R0. You need FYD, which is calculated from 0.87 times FYK. The FYK here is 500. That gives you FYD equals to 435. Next, you get the strength, the design yield strength of the steel bar, which is calculated by dividing the FYD with the modulus of elasticity of the steel. FYD is 435. Modulus of elasticity of the steel is 200 gigapascal. Substitute the value, you get the strength equals to 0.00218. To calculate 1 per R0, you need the effective depth. This effective depth is important. You must first know that the axis that you are designing for the column. In this case, it is uni-axial load acting in the minor axis. That means when we calculate the D, it is no longer on the basis of 300. it shall be on the basis of 150. So your D now, it will be calculated with 150 minus concrete cover 35 minus the diameter of the shear link 6 mm and minus half of the bar size, which refers to the question here, it is 16 mm. Then you'll get your D equals to 100.01 mm. Substitute the D, substitute the epsilon, you get 1 per R naught. And then you need to get the K phi. K phi is the creep factor. You need the effective creep ratio, and also you need a factor beta here. The beta is governed by FCK and also the slenderness ratio. FCK is given 30 Newton per mm square. The slenderness ratio given 48.5. That gives you beta equals to 0.1767. Next, you need to get the effective creep ratio. These two values are assumed. We simply adopt these two values, acquire the effective creep ratio, substitute them into the equations, you get the K phi. Now that we have the Kr, which is assumed to be 1.0, K phi calculated, and also 1 per R naught is also calculated. That gives you the curvature 1 per R. Substitute it into the equations for E2. You need also the C. C is a constant given as temp, and also the effective length of the column, that is 2-point-something meter as given in the question. Substitute the value, you get E equals to 26.8. Multiply the NED 49.12 kN. You have your N2 equals to 1.3 kN meter. Bear in mind that this M2 is not confirmed yet. Why is it so? It is calculated on the basis of the assumptions that Kr equals to 1.0. At the end of the day, it might not be equals to 1.0. Then you will need to do the corrections. In the case that it is equals to 1.0, then this N2 shall be confirmed. At the moment, we don't know whether it is confirmed or not, but we will proceed first, later and come back to check this M2 again. Now that we have obtained the M2, based on the equation here, we shall compare all these four components. First, we look at the M02. We have calculated earlier on 13.6. And then we look at the MOE plus M2, 11.3 plus 1.3. Next, we look at MO1 plus 0.5 M2. MO1 is 7.8 plus half of the M2. And then lastly, the M-min. The M-min, it will be the same throughout all types of column. None of the calculated value here should be smaller than M-min. It is calculated by multiplying the Asian loops times the eccentricity due to the construction's tolerance. It is calculated on basis of E naught equals to H per 30, and it needs to be greater than 20. Now this H here cannot be any value. It is in fact the dimensions of the column, but we have to determine by looking at the directions of the bending moment. The bending moment is now in the minor axis. That means this H here, it shall be on basis of the minor axis, which in this case is 150. 150 divided by 30. You get E naught equals to 5 mm. It is smaller than 20 mm. That means we will straight away take E node equals to 20 mm. Multiply NED 49.12. You get your M means equals to 0.98 kN meter. Compare the four components here. The largest value shall be the MED. Now your MED is equals to 13.6 kN meter. With the MED acquired, our next step it will be using the design chart in order for us to get the AS. Substitute the values into the two equations. The first one represents the y-axis and the second one represents the x-axis. You get these two values. NED is given 49.12 kN, BH 150 times 300, FCK 30 Newton per mm square. As for the second equations, the MED here we have calculated 13.6 kN meter divided by BH square. You will need to be careful with this BH square. The bending is in the minor axis. That means this will be the B and this will be the H. Therefore, B times H square and FCK is 30 Newton per mm square. Having these two values ready, now you need to refer to the design chart. There is a series of the design chart ranging from 0.05 to 0.25 in terms of the D2 per H ratio. You will need to calculate the T2 per H ratios for you to decide which chart to be used. Now how do you calculate D2? D2 is referring to the edge of the column to the center of reinforcement. This is calculated by having the concrete cover plus the size of the shielding plus half size of the steel bar. Concrete cover is 35. Shielding given 6 mm. Bar diameter 16 mm. Divided by 2. You get your D equals to 49 mm. Now you need to find the D2 per H. The H here shall refer to the minor axis, since we are designing the column in the minor axis. That means now D2 49 divided by the minor axis 150. That gives you 0.327. Now if you refer to the series of the chart here, the largest value it will be 0.25. You don't have any chart beyond 0.25. In this case, you can use the D per H ratio of 0.25 as the basis for you to do the design. Now you might want to ask, is it safe to do this? We know that the D2 per H ratio, if possible, we go for the accurate one. But obviously in this case cannot be done, since you do not have D2 per H ratio more than 0.25. To answer these questions, you may refer to the solutions that we did in our previous example. Remember that in our previous example, our D2 per H is 0.157. We do not have the chart for 0.157, but we do have the chart for 0.15 and 0.20. So the solutions was, we find the AS value on basis of 0.15 and we find another one on the basis of 0.2. Later we do some interpolations. We do the interpolations against 0.157 in order to conclude the final AS. Now if you observe the solutions, these are the values acquired from both charts. the chart of 0.15 is giving slightly higher value than 0.2. That means the smaller the ratio, the more conservative it is in terms of the amount of reinforcement. On this note, in the case that you do not like to do any interpolations, having the D2 per H ratio equals to 0.157, you can straight away use the value obtained from the chart of 0.15. That means you may go for the D per H ratio of smaller value than what is actual, but not the larger D per H ratio. The smaller the value, it would be more conservative. Now coming back to the question just now, our D2 per H ratio is 0.327. Is it safe to use the chart of 0.25? I guess you know the answer already. Yes, it is safe. It will be slightly more conservative. Since we do not have chart cater for this 0.327, therefore, using the chart of 0.25, it will be the best solution. Having the chart selected, we know the y-axis 0.036, the x-axis 0.067, 0.036 is somewhere here, 0.067 is somewhere here. It intersects at this point. Draw a 90-degree line and you start to estimate the locations. Referring to the curve where the intersections happen, it is between 0.1 to 0.2. It seems that it is quite close to the 0.2 line. Let's say now it ends up to be 0.19. In the equation here, only AS that we are not sure. The rest are given in the questions. To find the AS, you move all the nons to the other side. That means 0.19 times B, 150 times H, 300 times SCK, 30 divided by FYK, 500. Now you get your AS 513 mm square. Now we have the AS required in the column. Remember in our previous calculation, we do not know the AS provided and therefore we assume the KR. Now we have the AS required. We use this AS in order for us to compute the KR. Substitute this AS into the equations to determine the omega. FYD we have calculated, which is equal to 435. AC is the cross-sectional area of the column, 150 times 300. FCD we have calculated also from these equations, which is equals to 17. You get the omega, use the omega to calculate the NU, and then you calculate the N. NED 49.12 kN divided by the area of the column 150 times 300 times SCD 17. Now you have N, NU, and the N balance we assume it is equals to 0.4. Substitute the value into the equations of KR, and KR should not be greater than 1.0, which in this case, when you calculate this, the KR is actually more than 1.0 and it is kept in 1.0. Therefore, we will take the KR equals to 1.0. This value here, it will be the same as what we have assumed previously, where the KR equals to 1.0. That means when the KR here is the same, while the others are also the same, that means you will get the same curvature and subsequently you will get the same E2 and also M2. By now, we can more or less confirm the M2 is equals to 1.3 kN meter. And as a result, The design moment, it will be the same as the one that we have designed previously, equals to 13.6. And the required area of reinforcement, 513 mm square. Now you will need to provide the reinforcement bar. Minimum 4 units of reinforcement bar. 16 mm bar diameter is provided. You can try with 12 mm, but the rebar areas is insufficient. Therefore, you will need to increase the size of the reinforcement. 4H16 will give you 104 mm square, where your AS provided is now greater than AS required. That means the provided amount of reinforcement bar is sufficient. Minimum numbers of rebar sufficient, minimum bar size sufficient, AS provided is also sufficient. And then we calculate the AS mean. Use these equations to calculate the AS mean. You have your AS mean equals to 90 mm square. And then calculate the maximum bar area. Get your AS provided at 0.4 divided by the cross-sectional area of the column, which is 150 times 300. The reinforcement constitutes about 1.8% of the total cross-sectional area of the column, which is less than 4%. That means the AS maximum is not exceeded. At the lapping regions, the amount of reinforcement bar doubled, and it is less than 8%, and the AS maximum is also not exceeded. Next, we will deal with the requirements for the limb. This calculation step, it will be the same as our previous calculations. Ultimately, you're going to provide 6 mm diameter limb with the spacing of 150 for the column, and when come to the joint or the lapping regions, the maximum spacing it will be 75.